Okay, welcome to Friday's lesson video. So for those of you who are not here on Friday, we reviewed radiometric dating, which is one of the experiments that scientists use to determine the age of the Earth. So in order to understand that, first thing we got to talk about are what are atoms. Atoms are the basic building block of matter. So if you take a gold bar, for example, and you split it in half, and you keep cutting it in half until you can't cut it in half anymore, all you will be left with is an atom of gold, okay? Now, the Earth has many different types of atoms. We call those elements. For example, diamonds are made from the element carbon. Here's an image of a carbon atom, just a drawing. And diamonds are made of carbon. And we have a photograph of people mining diamonds in Zimbabwe. Now, interestingly enough, the pencil lead that's in your pencil is also made of a carbon atom. So that's just sort of showing you how different types of arrangement of these atoms can look differently. But anyway, the main thing is that the Earth has different types of atoms called elements, and you can find those types on the periodic table. And in fact, there are 118 different types, right? We have hydrogen, we have helium atoms, oxygen, sodium, chlorine, copper, and gold. They're all different types of atoms. So let's get into radiometric dating. So if you watched the video on Thursday night, you would have seen some of this. I'm just going over some key things. So first of all, the Earth is very old, right? But the question is, how old is it? And no one was around when the Earth was born or formed, so scientists have to perform experiments and gather evidence to determine the age of the Earth. And one experiment or evidence that scientists like to gather is called radiometric dating. And that's used to determine the age of rocks and fossils, which is used as evidence for predicting the age of the Earth. So let's talk about radiometric dating. What it is scientists use radioactive isotopes, which are just a type of atom, to measure the age of the Earth. So first, let's break this word down, because if you break it down, it makes sense. So radio refers to radioactive. So when you think of radioactive, you may think of a nuclear reaction, or a nuclear power plant, or a nuclear missile, or this symbol, right? So when you think of something that's radioactive, it's not stable. It's dangerous, actually. Now the word metric. Metric refers to measure, like meter, right? And there's different types of measurements, but in this case, it's specifically measuring time. And dating here refers to how old is it. So when I say dating, I'm not talking about that type of dating. I'm talking about how old it is, okay? So for radiometric dating, they're using radioactive isotopes to measure how old something is. So let's talk about radioactive isotopes. So isotopes are just atoms, but they have a particular mass and identity. Radioactive isotopes are unstable elements that undergo radioactive decay. We call that the parent isotope. So what you're starting with is going to be unstable, and it's going to decay or break down into what's called your daughter isotope. So the daughter isotope is stable, and so it's not going to break down any further. So here's an example. We have uranium, and this is unstable. See, it's glowing, it's radioactive. That's called your parent isotope. So you start with parent, and then the parent makes the daughter isotope. So lead is, when uranium decays, it decays into lead, Pb, which is your daughter isotope. So how do they use these isotopes to determine the age of something? Well, it all has to do with something called half-life. So half-life is the amount of time it takes for half of a radioactive isotope to decay. For example, if you started with 20 grams of a radioactive isotope, X, with a half-life of 3 days, in 3 days you'll have 10 grams of X. So if X has a half-life of 3 days, and you start with 20 grams of X, in 3 days you're only going to have half that amount, which is 10 grams. So let's talk about radiometric dating. Scientists use special equipment to sort of figure out the amounts of parent and daughter isotopes in a rock or a fossil. And once they know that, based on the number of parent and daughter isotopes, they can determine how many half-lives have passed since the rock or fossil was first formed, and thus the age of the rock or fossil. Now, the thing is that there's different types of isotopes scientists can choose from, and scientists must choose the correct one. So you want the half-life of the isotope to be not too short and not too long. And so if you look at this table here, you see there's carbon-14, potassium-40, uranium-238, and rubidium-87. They all have different half-lives. So carbon half-life is 5,730 years, whereas uranium is 4.47 billion years, okay? So if you want to study something from the Precambrian era, you're going to use uranium because its half-life is just the right amount. It's not too long, it's not too short. If you want to study something from the Paleozoic or Mesozoic, you're probably going to use potassium-40 because its half-life, again, it's not too long, it's not too short. It's just right. And if you want to study something from the Cenozoic, you would use carbon-14 because, again, its half-life is perfect. Not too long, not too short. Okay, so how exactly do they do that? How exactly do they determine the age based on the half-life? Let's say, for example, you find a rock. And this rock you think was around since the Earth was formed, but you're not sure. And you determine that the rock has 1, 2, 3, 4, 5, 6, 7 lead atoms. So Pb, remember, is lead. And only 1 uranium. Now, what scientists assume in this case is that the lead atoms, the blue ones, came from the uranium. So all of these blue lead atoms used to be a yellow uranium atom, okay? So they're saying that the rock actually must have started with 8 uranium atoms because there's a total of 8 atoms here, so there must have been 8 uraniums over here. All right, so then they know, well, the half-life of uranium is 4.47 billion years. So if the original rock was all uranium, and it had 8 uranium atoms, then in 4.7 billion years, you're going to have half of 8, which would mean that you have 4 uranium atoms, and then 4 leads, because remember, the uranium will decay and form a lead. So this uranium, for example, turned into this lead atom, okay? Oops. So right now we have 4 uraniums and 4 leads, but our rock today has 7 lead atoms and 1 uranium. So that means that another half-life must have passed by, and so in this case, the 4 uraniums that are remaining, they're going to decay. 2 of them, half of them, or 2 of them will decay, leaving you with 2 uraniums and 6 lead atoms. But we're still not where the rock was today. The rock only has 1 uranium and 7, so it must have been another half-life. So of these 2, half of them decayed, leaving you with just 1 uranium. So now when we look at the age of this rock, we would say, oh, okay, in order to go from all uranium to 7 lead atoms and 1 uranium, 4.7 billion years passed, and then another 4.7 billion years, and then another 4.7 billion years. That means that the total time is going to be 4.7 plus 4.7 plus 4.7 billion years, or 3 times 4.7 billion years, which gives you 14.1 billion years. So that means that this rock is 14.1 billion years old. And that's how scientists use half-life to determine the age. Now, did you know that there is the world's oldest rock? It's a zircon crystal from Australia, and it's dated to be about 4.4 billion years old. Now, most rocks are actually younger than that. Even though the Earth is about 4.5 billion years old, most rocks are younger, and that's because, remember, the crust, Earth's crust, is constantly being recycled through what's called the rock cycle. So what do I mean by that? The Earth's crust, remember, is broken into plates, sort of like a cracked egg, and those plates move. And when they crash into each other sometimes, the denser plate will go under the surface of the Earth. And when it does, it's really hot down there, so it melts it and it destroys it. And then it can come back up through lava from a volcano. So it's being recycled. That means that most of the Earth's crust is recycled rock. It's not rock from when the Earth was first formed, because it has been recycled. All right, so we talked about radiometric dating. What other evidence do scientists use? Is radiometric dating enough? No. So besides radiometric dating, scientists study impact craters from meteors and asteroids. And they study impact craters not just on Earth, but also on the Moon and other planets, because they assume that they believe that the planets were formed around the same time. They also study rock layers. So you see sometimes the rocks have different layers and the composition of those rock layers. They also use their understanding of current changes. So the Earth is constantly changing, and by observing changes that happen today, they can make predictions about changes that may have happened in the past. And they study fossils and artifacts. So all these different types of evidence are going to be used to form theories that describe the age of the Earth and how it was formed. All right, so main summary. Because no humans were around when the Earth was formed, scientists must gather evidence to determine the age of the rocks, fossils, and artifacts. One of the strongest forms of evidence is radiometric dating. Radiometric dating is where scientists use radioactive isotopes to measure the age of the Earth. Now remember, other forms of evidence include impact craters, composition of rock layers, understanding current changes, and studying fossils and artifacts. Okay, so that is it for this video on radiometric dating and evidence for the Earth. Next week, you will take some notes in your notebook to sort of summarize what you covered here. All right, that's it for this video. Have a quality day.